It is 11 billion miles from home. No light reaches it in less than 19 hours. No signal, no matter how strong, arrives any faster. For a machine built in the 1970s, using less computing power than a modern key fob, it is still awake, still listening, still speaking, one faint whisper at a time, into a silence that has no edges. And in that silence it found something nobody was ready for. Not a signal, not a ship, not a voice, something quieter and in some ways stranger, a change in the fabric of the space around it, a discrepancy between what physics predicted and what the instruments actually recorded. The kind of anomaly that doesn't explode across headlines in a single day, but instead sits in the data, waiting for someone to notice that the universe just did something it wasn't supposed to do. This is the real story of Voyager 2, and the discovery that quietly forced scientists to reconsider what protects our solar system and what doesn't. The date was November 5, 2018. At the Jet Propulsion Laboratory in Pasadena, California, a small team of scientists watched a plot on a screen. It was not dramatic to look at. Just a line, plasma density readings from an instrument called the Plasma Science Experiment, ticking upward in a way it hadn't before. Around it, cosmic ray counts were climbing too. Solar wind particles were falling away to almost nothing. Voyager 2 had done something only one other human-made object had ever done. It had left the heliosphere, the vast bubble of charged particles blown outward by our sun, and entered interstellar space. 6 years earlier, its twin, Voyager 1, had made the same crossing. But Voyager 1's plasma instrument had stopped working decades before, back in 1980. Scientists had been forced to infer its position indirectly, through secondary evidence, educated guesses stitched together from limited data. Voyager 2 was different. Its plasma instrument was still alive. For the first time in human history, scientists could directly measure what interstellar space actually felt like. Not from a model, not from an extrapolation, but from a machine physically sitting inside it, sending back real numbers. And the numbers were not what anyone expected. Here is the scale of what we are talking about. The heliosphere is not a wall. It is a pressure boundary, roughly 11 billion miles across, created by the solar wind pushing outward against the thin gas of interstellar space. Inside it, our sun's influence dominates. Outside it, the galaxy takes over. Voyager 2 took 41 years to reach that boundary. It is traveling at roughly 34,000 miles per hour, fast enough to cross the continental United States in about 4 minutes, and it still needed 4 decades to get there. Once it crossed, everything about its environment changed within a matter of hours. Solar wind density, which had been trickling to nearly nothing, dropped off a cliff. Cosmic ray levels, shielded for decades by the heliosphere's protective bubble, spiked upward by more than 5% in a single day. For a moment, that was the headline. Confirmation. A milestone. The second spacecraft in history to leave the solar system's protective bubble. But then researchers looked again, and the deeper they looked, the stranger it became. The first anomaly showed up almost immediately in a paper published in November 2019 by a team led by plasma physicist John Richardson at MIT. Voyager 2's instruments recorded that the plasma just outside the heliosphere was roughly 10 times denser than the plasma inside it. That part, on its own, matched theoretical predictions. Scientists had expected interstellar plasma to be denser than the thinned-out solar wind near the heliosphere's edge. What they had not expected was the specific density Voyager 2 recorded, noticeably higher than what Voyager 1 had indirectly implied when it crossed 6 years earlier, in a different location at a different angle through the boundary. 2 spacecraft, 2 separate points along the same bubble's edge, 2 different pictures of how thick that boundary actually is. The heliosphere, it turned out, was not a smooth, symmetrical sphere. It was lopsided, compressed on one side, stretched on the other, and the exact reasons why were not fully understood. Anomaly 1, an asymmetric boundary that didn't match the clean model scientists had built for 40 years. Then came Anomaly 2. Roughly 3 years before Voyager 2 physically crossed the heliopause, its magnetic field instrument recorded something unusual, a slow, gradual increase in magnetic field strength, far earlier than any existing model predicted it should appear. Some researchers described it as evidence of a pressure front, a kind of long, drawn-out compression zone extending outward from the heliosphere's true edge, farther into space than anyone had accounted for. In other words, the boundary of our solar system's protection does not begin where the map said it began. It begins earlier. It fades in, rather than snapping into place. And that raised an uncomfortable question. If the edge of our protective bubble is not where models say it is, if it is fuzzier, weaker, and less predictable than assumed, what does that mean for how well it actually protects us? Then, in 2019, came the detail that made even veteran scientists pause. Voyager 2's plasma wave instrument, originally designed and overseen for decades by physicist Don Gurnett of the University of Iowa, picked up something the team had not planned for. As the spacecraft moved deeper into interstellar space, it began detecting oscillations in the surrounding plasma, essentially vibrations that let scientists calculate density from a distance, the same way you might guess the depth of a well by timing an echo. Those oscillations revealed that the plasma just beyond the heliopause was not just denser than inside the bubble. It was increasing in density the farther Voyager 2 traveled outward. That was not part of the plan. The leading models of interstellar space, built from decades of remote observation, treated the local interstellar medium as relatively uniform, a thin, mostly steady soup of particles drifting between star systems. Voyager 2's direct measurements suggested something closer to a gradient, a density that changes the deeper you go. If that pattern holds, it implies our solar system is not simply floating in open, uniform space. It may be sitting near the edge of a denser cloud of interstellar material, one that the heliosphere has to push back against harder in some directions than others. This is where the story usually splits into two paths, and it is worth being honest about both. The first path belongs to a small vocal minority of researchers who have used exactly this kind of anomaly, asymmetric boundaries, unexpected density gradients, earlier than predicted pressure fronts, to argue that our solar system's protective bubble may be entering a period of long-term weakening. The theory goes further in its more speculative corners, that as the sun moves through the galaxy, it periodically passes through denser interstellar clouds, and that these encounters compress the heliosphere down to a fraction of its usual size, exposing the inner solar system, including Earth, to sharply elevated levels of cosmic radiation for centuries at a time. Proponents of this idea point to ice core data on Earth showing spikes in certain radioactive isotopes at irregular intervals over the past several 100,000 years, and argue these spikes correlate loosely with theoretical passages through denser regions of the galaxy. It's the kind of idea that sounds enormous. Civilization scale, the sort of thing that reframes Voyager 2's plasma readings as an early warning rather than a data point. Here is the second path, the grounding one. The overwhelming consensus among heliophysicists is that Voyager 2's findings, while genuinely surprising, do not indicate any imminent danger to Earth. The density variations detected are real, and they are forcing real revisions to heliosphere models. But the timescales involved in any meaningful compression of the solar system's protective bubble due to interstellar cloud density are measured in tens of thousands to millions of years, not centuries. The ice core isotope spikes, cited by more speculative theories, have far more established explanations rooted in solar activity cycles and geomagnetic field variations, not interstellar cloud passages. In plain terms, the boundary of our solar system is stranger, lumpier, and less symmetrical than the textbooks assumed. That is a real, published, peer-reviewed finding. It is not, on its own, evidence of a looming catastrophe. What it is evidence of is something almost more unsettling in a quieter way, how much we still don't know about the space immediately outside our own front door. Voyager 2's plasma instrument is, as of this recording, the only functioning instrument of its kind past the heliopause. Voyager 1's equivalent stopped working in 1980. When Voyager 2's power eventually runs out, engineers estimate some point in the early 2030s, as its plutonium power source continues its slow decay, humanity will have no working direct sensor in interstellar space. Not one. Every future measurement, until a new mission is designed, funded, built, and launched, will once again rely on models and inference. There is a sobering detail buried in that timeline. In August 2023, ground controllers at JPL sent Voyager 2 a routine command sequence. A single incorrect parameter tilted its antenna 2 degrees away from Earth. At a distance of 12.3 billion miles, 2 degrees was enough to sever contact entirely. For a week, the most distant functioning spacecraft humanity has ever built was, for all practical purposes, gone. Silent, unreachable by any conventional signal. Engineers made the decision to attempt what they internally called an interstellar shout, transmitting an extraordinarily powerful command through the deep space network aimed at the calculated last known position of the spacecraft in the hope that even a fraction of a degree of residual antenna alignment might catch it. On October 22, 2023, Voyager 2 answered. It had heard the shout, it reoriented itself, and it resumed sending data, the same data that continues today, to quietly rewrite what we thought we understood about the edge of home. Think about the scale of that for a moment. A signal sent from Earth, traveling at the speed of light, still took over 18 hours to arrive. Voyager 2's confirming reply took another 18 hours to come back. An entire day and a half spent waiting to find out whether humanity's most distant machine had simply gone deaf, or whether it was still out there, still listening, still willing to talk. It was still there. It is still there right now, this moment, moving further from us at roughly 9.5 miles every second, sending back readings from a region of space where the rules our models were built on do not quite hold. There is something almost uncomfortable about how ordinary the discovery looks on paper. No flashing lights, no dramatic image, just numbers on a plasma density chart, ticking slightly higher than they were supposed to. But those numbers describe something enormous. They describe the actual shape of the bubble that has sheltered every human being who has ever lived, every war fought, every civilization built, every sunrise witnessed, sheltered it from a galaxy filled with high-energy cosmic radiation that, in sufficiently large doses, damages living cells and interferes with the kind of complex chemistry that makes life possible at all. For billions of years, we assumed that bubble was simply there, blindly, passively protecting us, its exact shape and strength a settled fact of astronomy. Voyager 2 found out it isn't settled. It's lopsided. It's still being measured for the first time by direct instruments as you listen to this sentence. And there are parts of its structure, the slow building pressure front, the density gradient beyond the boundary, the possibility of a nearby denser interstellar cloud, that scientists are still actively working to explain. Nobody expected the edge of the solar system to look like this. Everything about how we modeled it before 2018 assumed a cleaner, more symmetrical shield. What Voyager 2 sent back instead was a warped, uneven, slowly shifting boundary that behaves less like a wall and more like a tide line, advancing and receding depending on direction, pressure, and forces we're still working to fully map. You need to understand what that means for the next generation of space exploration. Every future interstellar probe, every long-range mission design, every calculation of radiation exposure for a hypothetical crewed mission beyond the heliosphere now has to account for a boundary that is far less predictable than the one described in textbooks as recently as a decade ago. There is a strange kind of humility in that. A machine built with 1970s hardware, running on a fraction of the processing power of a pocket calculator, managed to outperform 4 decades of theoretical modeling, simply by being there and by refusing to stop listening. Stay with me for the last piece of this, because it's the part that tends to stick. Voyager 2 carries a golden record, a message, etched in sound and image, intended for anyone or anything that might one day encounter it. Greetings in 55 languages, music from cultures across the planet, the sound of a heartbeat, of ocean waves, of a mother's first words to her newborn child. That record is not aimed at us. It was built for a future that may never arrive, addressed to a recipient that may not exist, drifting now through a stretch of space stranger and lumpier than the people who built it ever imagined. And somewhere in that same drifting instrument package sits a plasma sensor, still faithfully doing its job, quietly telling us that the boundary between us and everything else is not the clean line we drew on old diagrams. It's a soft, shifting, asymmetrical edge, one we are only now, for the first time in history, measuring directly instead of guessing at. By the end of Voyager 2's working life, sometime in the next several years, that direct measurement will go silent again. And the next real answers about what lies just beyond our door may not come for decades, which leaves one open question, the kind investigative science stories are supposed to leave you with. If the edge of our solar system is this uneven, this asymmetrical, this different from what 40 years of models predicted, what does that tell us about the thousands of other stars in our galaxy, each presumably wrapped in a bubble of their own, each shaped by forces we've only just begun to measure around one single, unusually fortunate example? We don't know yet. For now, if stories like this, the quiet, data-driven kind, built from real missions and real anomalies rather than speculation, are the kind of thing you want more of, sticking around for the next one is the best way to see where this leads. Voyager 2 is still out there, still transmitting, still 11 billion miles from home, listening for whatever comes next.